Okay, so this is the integral form, and let's specifically write down this integral form of the PDE, which is this equal to this plus this, for a scalar conservation law in 1D. Okay, so for scalar conservation law in 1D, we have d dt of the integration over an arbitrary volume in over arbitrary contiguous volume in 1D. What does that mean? What is a contiguous volume in 1D?
Line segment?
It's an interval, yeah, line segment. So from A to B, right? So let's say omega has to be equal to something like AB in 1D. So this dv becomes just the dx, right? So would be equal to, okay, so what is a boundary integral in 1D? Yeah, wait, how do you integrate? I mean, what is the boundary of an interval A and B? It's just a point A and point D, right? Point B, right? And what is the unit normal n?
1 and -1.
Yes, at B n is equal to 1, and at A n is equal to -1, right? So these are the outward normal, right? So let's just do this integral. This integral becomes just the two numbers added together, right? At B, this is actually negative because I have minus n. At A, it is positive. So let's write the positive term first. It's fu at A minus fu at B, right? That's the boundary integral in 1D. And then plus integration A over B g dx. All right. So that's the integral form of my conservation law. It's actually the closest to physics form of the conservation law that works no matter U is differentiable in space or not. Huh?
Why are you doing the line case?
Why am I doing?
The line case.
Oh, I'm doing 1D case because that's the first equations we're going to be solving using numerical methods, right? And it's also simpler to visualize and to think about how the solution should behave. Yeah. So this works if U is not differentiable. It even works if U is not differentiable in time, right? Why? Because even though I'm taking the time derivative here, I'm taking the time derivative of an integral. So even though if you look at this solution, U is not differentiable in time, because if I go upward in t with a fixed x, my U is also discontinuous. But it also works because this is not just the U, it's U integrated over volume. As long as you start integrating over volume, and as long as the discontinuity moves at a finite speed, the time integral is still, the spatial integral is still continuous and differentiable. Okay, does that make sense? Okay, so we have three forms so far. We have the conservative form, primitive form that works for smooth regions, and we have the integral form that works no matter if the solution is smooth or not, right? So now it becomes pretty obvious if you want to solve an equation with potential discontinuities, which form you should discretize if we want to use a numerical method. We want to discretize the integral form, right? That's why finite difference isn't the first choice you would use to solve equations like that. And the finite volume is going to discretize directly this integral form. Okay, do we still remember what finite volume represents? We had at the FD demo, do I still have it here? Right. In finite difference demo, remember if we have a function, it only stores the value of the solution. That's what we used before finite difference. If you do finite volume, let me make a new figure. If you do finite volume, let me try to draw the same function. What it discretizes is, Okay, so let me finite difference, finite volume. What it stores are not the function values at any particular points, but the volume averages, right? And now we start to see why. Because the volume averages are closely related to the integral of a solution over a domain, right? If this is my A and this is my B, the volume average is just the volume integral divided by B minus A, right? A very simple linear algebraic relationship between what we store and what is appearing in the integral form of the equation. So in finite volume, what we'll be approximating is actually not the differential operators, because there are no special differential operators in the integral form. What we'll be approximating is actually these guys, right? Because actually now we have lost any values of the function at any point. I mean, we are not storing the value of u at any point, not in A, not at B. So we cannot directly evaluate f of u at A or f of u at B. We have to figure out some way to approximate the point-wise values of the function from these volume averages, which we actually store in the computer. So that's basically how finite volume works as opposed to finite difference. Okay. All right. So that's the integral form of this equation, and let's use the integral form to do something first, to analyze the behavior of discontinuities in the solution, to analyze how these shockwaves are supposed to behave. Why are they moving around? And can we determine from something from the differential equation which direction should they move and at what speed?